let's go through a couple of AP-style questions that have come from previous AP tests that might help you better to understand the relationship between stoichiometry and thermochemistry. So this is a question taken from the 2018 AP Chem examination. Here's the balanced equation. It's not a net ionic reaction. As you can see, it's got a bunch of sodium ions fooling around here. And the experiment is to determine the value of the enthalpy change, the delta H for 1 mole of reaction, for this oxidation reduction reaction. So we will go ahead first of all to this problem. From the graph, is this an endothermic or exothermic reaction? So you look at the graph and you see the temperature has gone in what direction? Right, up. Temperature of the surroundings is increasing. Remember, we don't measure directly the system, the chemical reaction, we measure the surroundings. The heat coming is coming out of the chemical system into the surroundings. That's what's making the temperature increase. So this is an exothermic reaction since heat is coming out of the system. What's the temperature change including sign? Well, the temperature change is positive. Delta T is greater than 0. We worked that out already. And when we subtract the high temperature minus the low, always final minus initial, we get plus 12.5 degrees Celsius. That's it. Where would the reaction enthalpy be reported in the equation above? Well, his system is losing heat to the surroundings, so the energy of reactants is greater than that of products. Delta H then is acting as a product, and therefore it's going to be on the right side of the equation, so we'll put delta H here. If it was endothermic, it would be on the left side of the equation. But the delta H is coming out, therefore it's like a product. What's the sign of the enthalpy change of the chemical system? Well, the system's losing heat to the surroundings. We determined that already. So delta H is less than 0. Remember, the temperature change is positive. That means that the change in the system is negative. Enthalpy change in the system is negative. How will we show this in customary format? Well, as you know, we report it as delta H equals. Once more, the system's losing heat. Therefore, products minus reactants is a negative number. So delta H is a negative number. And that's how it would be reported. Now, if the mass of the reaction mixture is 15.21 grams, what's the magnitude of the heat energy, Q, that's released? And they're telling us the specific heat of the reaction mixture is 3.94 joules per gram degree Celsius. Now, you'll notice that's not the same as water. It's a little less. But they're ignoring the heat that's absorbed by the calorimeter, by the styrofoam surrounding it. So we're measuring heat released, that's Q. Q is equal to mc delta T, or MCAT. So the mass of the surrounding mixture is 15.21 grams. The C is 3.94 joules per gram degree Celsius. That's what you see here. And the temperature change is positive 12.5. So the Q is going to be positive. We already kind of worked that out in our heads. So that's 749.1 joules, but we've only got 3 significant digits in the temperature, in the change, the C, the specific heat. You've got 3 significant digits in the temperature change, so 4, 3, and 3. You can only have 3 significant digits, so plus 749 joules. That's Q. Heat is released, so Q is positive. Using the balanced equation, determine which reactant is limiting. Now we're going to a different situation. And we've gone ahead and put Q up here at 749 joules. All right. Millimoles of reactant, molarity times the volume. And here's the other reactant, and here is the product. I'm sorry, here's the other reactant. So there are 3 reactants. And you've got 2.50 millimoles of all of them. Now, which one's limiting? Well, the answer is, which one will run out first? Just look at the equation and tell me, which one of these is going to run out before the other 2? And the answer is obvious, I think. The NaOCl, the sodium hypochlorite, that's bleach, disappears 4 times faster than the thiosulfate and twice as fast as the sodium hydroxide. So when all of this is gone, we've only used up 1.25, half that, of sodium hydroxide, and 1.87 millimoles of this are left over. Thus the limiting reactant is right here, the one that's used up fastest. So we use all of that up. We use up 1/4 of this. We use up 1/2 of that. We are left with 3/4 of our original here, none of the sodium hypochlorite, and 1.25 millimoles of the sodium hydroxide. Now, how much product do we get? Let's look at that. Well, this is the same as that, and therefore, when you use up 2 moles of this, you're going to get 2 moles of that. So this is a plus 1.25. The 4 sodium chlorides means, since you had 4 sodium hypochlorites, you're going to get the same number of millimoles of appearing sodium chloride as disappeared of the sodium hypochlorite, and then the coefficient here and here are the same, so when you lose 0.63 of this, you gain 0.63 of that, and that's how much you have at the end of the reaction. So, using the balanced equation, your answer to part C, calculate the value of the enthalpy change in kilojoules per mole of reaction, including an appropriate algebraic sign. All right, so we're going to go back here. We had 749 joules of heat released, and delta H then is what we're looking for. Always consider what constitutes a mole of reaction. And here's the definition. 1 mole of reaction has occurred when the appropriate numbers of moles of substances specified by the stoichiometric coefficients on the left-hand side of the equation are converted to the substances on the right-hand side. When the change in the thermodynamic property is given for a particular chemical reaction, that always refers to a mole of reaction. Well, when you look at those 2 sentences, you could get a headache. But the plain fact is, we're going to look for the 1 coefficient, because when 1 mole of this is gone, then 1 mole of reaction has occurred. A mole of reaction then happens when 1 mole of thiosulfate reacts with 4 moles of hypochlorite and 2 moles of the hydroxide. All right. The Q released in 1 mole is the Q produced by the complete reaction then of 4 moles of sodium hypochlorite, because that's the only way we can get 1 mole of this to react. So what's Q in kilojoules per mole? So we're going to increase all of this to stoichiometric numbers and use up all of that. We are then going to multiply by the appropriate numbers and see how much of the product we produce. And for 4 moles of sodium hypochlorite here, you're going to produce 1198 joules of energy. So that's the answer for 1 mole of reaction. Q is produced. So the Q released in 1 mole of reaction is a Q produced by the complete reaction of 4 millimoles of NaOCl. And we're going to remember that we were working in joules before, and all you have to do is put a K in front of this if you're working with moles instead of millimoles. So Q is 1198 joules per millimole, or 1198 kilojoules per mole. That's 1.203 sigdigs times 10 to the third kilojoules per mole. Therefore, delta H for 1 mole of reaction is negative 1.2 times 10 to the third kilojoules per mole. Last question from the test. The magnitude is this, calculated from the results of the experiment, the same as the result in part E2, the one we just worked out. If you have this number of volume and concentration. You can think about that one. I'll put it back up here so you can take a screenshot or something. The enthalpy change in kilojoules per mole of reaction calculated here is the same as the result calculated in the prior slide. It's easy to explain, but I'm going to tell you what the answer is.